This is part 3 of the Module 9 lecture. So now in here, we're going to start looking at how to test the hypothesis to compare the variances of two independent populations. Again, we're going to follow the same procedure that we learned in Module 8 when we compare the mean and the single mean and a single proportion. So we're going to see how we are going to state the null and alternative hypothesis, and then we're going to see how to calculate what distribution to use, what test statistic needs to be calculated, and how we're going to use that test statistic and the significance level to define the rejection regions or to define a p-value. And then the decision as before will be the same. All right, let's look at this. So now when we're comparing two variances, for example, when we have a two-tailed test, under the null hypothesis, we're assuming that the variances are equal. And under the alternative hypothesis, we say that the variances are not equal. But again, if you remember in the previous section, we talked about the F statistic, which is a ratio of variances. So we need to translate this equality or inequality of variances into equality and inequality of a ratio of variances. So in here, we put the variance for the population 1 at the top, and then the variance for the second population at the bottom. And if they are equal, this ratio should be used 1. But if using the same ratio, and if these two variances are not equal, then this ratio should be different from 1. Now, in the case that we have a right-tailed test, again, you see that we're looking at the first variance to be larger than the second variance. And under the null hypothesis, you have either the equality or the first variance is smaller than the second variance. And then translating that into ratios, we have the ratio of the first variance to the second variance is less than or equal to 1, using this inequality. And then the ratio of the first variance to the second variance is larger than 1. So variance 1 is bigger than variance 2, so that ratio must be bigger than 1. Now, if you have a left-tailed test, now in this case, you know that the first variance is smaller than the second variance. And then under the null hypothesis, the first variance is going to be larger or equal to the second variance. Changing these two hypotheses into a ratio, then the hypothesis becomes as you see, variance 1 is bigger than variance 2 under the null hypothesis, so this ratio must be larger or equal than 1. Under the alternative hypothesis, variance 1 is smaller than variance 2, so the ratio of variance 1 divided by variance 2 must be less than 1. So these are how we're going to state the hypothesis depending on the situation, and we will have the two-tailed hypothesis, the right-tailed hypothesis, and the left-tailed hypothesis, now stated as ratio of variances. All right, so if we have two random samples drawn from two independently normal distributions, then the F statistic, which we defined in the previous section as this, will follow an F distribution with degrees of freedom of 1 and degrees of freedom 2. Now, and this note is very important to keep track of the degrees of freedom. So degrees of freedom 1 goes with the sample variance in the numerator, and the degrees of freedom 2 goes with the sample variance in the denominator. Now, under the null hypothesis, you can see that we have the equality sign right here. So there is, for two-tailed, there is equality. For right-tailed, there is the equality as well. And the left-tailed, we have the equality symbol there. So we're here that this ratio is, we're assuming that under the null hypothesis that this ratio of variance is equal to 1. So if you take that into account, so this ratio here, the denominator of the original F statistic is 1. So the test statistic, the F statistic simplifies what we call the test statistic, and is just a ratio of the sample variances. The same thing. The variance in the denominator has its own degrees of freedom, and those will be the degrees of freedom of the denominator. The variance in the numerator, that will go with the degrees of freedom on the numerator. So we need to keep track of which variance is in the numerator and which variance is in the denominator. Now, notice that the left tail test can be changed into a right tail test by just reversing the inequality. So in here, I have the variance 1 being larger or equal than variance 2. Well, I move the variance to the other side, and so the inequality reverses. The same here. So I move the variance to the left side of the inequality and the first variance to the right side of the inequality. And so the symbol, the inequality reverses. So translating this to the ratio of variances, now I have variance 2 in the numerator, variance 1 in the denominator, and that ratio is less than 1. Now variance 2 in the numerator and variance 1 in the denominator, well, that ratio is bigger than 1. So now I change it into a right tail test. This is very important because our tables are looking at probabilities to the right side. Table 7. So we impose always the conditions that the larger variance goes in the numerator, in the denominator, and the larger variance goes in the numerator, and the smaller variance goes always in the denominator. So that the f value is bigger or larger than 1, and that forces us to look at the right side of the distribution. So if you have a one-tailed test, and that one-tailed test is telling you which variance is the larger, well, then that variance will go in the numerator of the f statistic. If you have a two-tailed test, we don't know which one is larger. So we're going to look at the point estimate, the variance from the sample, and the larger variance, the larger estimate is going to go in the numerator and the smallest estimate in the denominator, so that we maintain this idea that the f statistic is larger than 1. And that will force us to look at the rejection regions and always to look at the right side of the distribution. And again, this is because we're using table 7. We're not using software. So if we use a software package, it doesn't matter which side, how you have the variances. You can always find the right value. So we're doing this to stay with the right probability on the probability to the right of the f value that is given by table 7. All right, so the rejection regions for a value of alpha and an f distribution with degrees of freedom 1 and degrees of freedom 2. So if you have a right tail test, so the rejection region is if the f observed value is larger than the f value for alpha with the corresponding degrees of freedom. If you have a two-tailed test, now we have two rejection regions, one to the right and one to the left. And to the right is for alpha divided by 2, and for the left is 1 minus alpha divided by 2, with degrees of freedom 1 and degrees of freedom 2. And always remember, degrees of freedom 1 corresponds to the variance in the numerator, and degrees of freedom 2 corresponds to the variance in the denominator. All right, so if we decide to use the critical value approach. If we like to use the p-value approach, well, again, once we know the p-value, we will reject the null hypothesis if the p-value is less than alpha. And we will fail to reject the null hypothesis if the p-value is larger than alpha. Again, this approach, we will not use it for the comparison of variances. But if you're curious and you would like to get the exact p-value, here are the formulas for Excel where you can find the p-values. And the reason we're not going to discuss the p-value is because now the table 7 is even skimpier than table 6 for the t-distribution. So now establishing probability bounds, there are going to be too gross a bound to really be able to determine if we can reject the null hypothesis or not. All right, so with this, I stop this recording. In the next section, we're going to now look at an example.